Hi. I want to talk to you today about um, hypothesis testing and in the context of inferential statistics. Um, this chapter on hypothesis testing is fairly conceptual rather than based on computation. You don't have to do any computation at all, basically, in this chapter. But you got to think about some concepts that I think are really crucial in concepts. Um, Put this back in the context of inferential statistics. The first unit we worked on was all descriptive statistics. It just described what's there. It's like, this is what we got. The second unit looked at probability, which asks you to start thinking about, given what we've got, what's the likelihood of something happening, and looks at relative probabilities for things. This unit starts saying, given what you've got, how do you make a step up and develop some inferences about that stuff? And what it does, it brings us to a kind of crucial question. This is somewhat a philosophical question, but it's a core question here, which is, how do you know something? How do you know something is true? Aside from, well, I believe it, so it must be true. There's too much of that going on right now in this country. The question is, how do you know something is true? How do you feel like, what allows you to say, I think there's evidence that this is true? And what do we mean by evidence in the process? And that gets us into the whole process of hypothesis testing. We have something we think is true, and we want to do some sort of test or experiment or something to see whether or not it's true. We have a hunch about something. We think we believe something, but we don't know. But it seems like it ought to be true. And so we start doing tests or experiments for it. And that's part of the definition of statistics, is that we do experiments or tests to find out about things, and we use a number base for doing it. We do that to solve problems or make decisions about things. The core piece in this process is we got to think about sort of, what does it mean to do an experiment? And to do hypothesis testing, one of the things we do is we start off by developing what we call a null hypothesis. We assume that the thing we believe is false. We start off by saying, I think such and such, but the null hypothesis is that that's not true. I use this example in the chapter this week a lot. There's a test out called the PHQ-9. And what the PHQ-9 does is a series of questions. And if you ask the person these questions, and they get a score of, say, above 20, I forget what the actual score is, but if they get a score above 20, for instance, it's very likely that they are depressed. And the reason they do this is they do this a lot in medical settings and family practice medical settings, for instance, that what happens is they talk to somebody and think, oh, this person sounds like they're depressed, hypothesis. So let me test. And what they do is they get out this little questionnaire and they ask the people questions. And at the end of the time, you get a score. And if you get a score, like I say, above a certain level, it says, yeah, that person probably is depressed. That's the administering the PHQ is, in fact, an experiment, or it's a test, basically. And what we're trying to do is say, well, is that true or not? If I were going to test this, for instance, I worked in a family practice, well, how good is this PHQ-9? I would do a series of administrations of this test, and then I would at some point stop and check with the person. It's like, are you in fact depressed, or does the person have a diagnosis already of depression? I mean, there's some ways of doing it. But in the immediate case, what you have is you have an individual sitting here, and I've got a piece of data that says this person is likely depressed. then what happens? Um, well, actually, we also, second after we have our null hypothesis, we have an alternative hypothesis, what I really believe. Generally, if I'm giving you the PHQ-9, I'm thinking, yeah, there's something here. There's something I ought to check in this thing. Actually went in for a routine checkup at one point with a nurse practitioner, and she did asked me a number of questions, and then at one point she went out to do something, and I looked over my file, so I reached over and looked through my file a little bit to see what was in what she had about me in this file, and I noted there was a PHQ in there which was not administered. There's nothing on it, and I asked her about it when I came back, like, why didn't she use a PHQ with me? And she said, there's no indication at all that you're depressed. That's a waste of time, I think. I went, reasonable thing. Her intuition was that I was not depressed and didn't see any reason to go ahead and test me to see whether or not I was. We do experiments to test ideas. And then we try and find out, was our test correct or not? And what we want to try and do is we want to for instance, if I was this nurse practitioner and I gave a client this test, my null hypothesis is this person's not depressed. What I really think is they are, but what I'm trying to do is get some evidence to reject the null hypothesis. And what comes out of it then is we get right here some different types of errors. If the test says or experiment says you can reject it, for instance, you get a score above a certain point, and that says yes, the person does, so I can reject my null hypothesis, which is you are not depressed. If in fact my alternative hypothesis, which is that you are depressed, is true, then I've made it a correct decision. If I've said, nope, you're not depressed, you are depressed, which is rejected, again, my null hypothesis is that you are not depressed. My hunch is that you are. So rejecting the null hypothesis is accepting your hunch. If your hunch is correct. My hunch is you have depression. You actually say you're depressed. Bingo, I win. The other possibility is the thing comes back and gives you a score of 12. What that would say is I had to accept the null hypothesis. You're not depressed. If I'm correct, that's fine. If you are in fact are not depressed, then the null hypothesis is true, and my test says is true. So that gives me a correct decision. So I've got two kinds of correct decisions. One is when I say, I think the null hypothesis was false, which means that alternative hypothesis is true, or that the null hypothesis is true, and I accept it. So there's two possibilities here. The upper left and the lower right here are the two good possibilities in here. The other ones are the different types of errors. Let me go through this a little bit using the depression example again. Reject the null hypothesis means I think you've got depression. And I talk to you and you're going, nah, not at all, Steve, you missed. That's a type 1 error. I think something's true, but it's not. The other type of error is I accept the null hypothesis. I accept that, I mean, you get a 12, and I go, well, that says you're not depressed. Thank you very much. Have a good day. And you walk out and say, boy, he missed something because I really am depressed. I made a type 2 error here. I accepted my null hypothesis when it was not true. Now, one of the questions is, here's one of the key things in this as you think through this stuff from a theoretical basis. As type 1 errors go up, type 2 errors go down. As type 2 errors go up, type 1 errors go down. You either tend to make more of one kind or more of the other kind of error. There's always errors in every testing. No testing is 100% correct all the time. There is this comes back to a concept we've talked a bit about in the class. There's a thing called natural variation. And just who knows what is, with the phase of the moon or the way the wind's blowing or what somebody said to you before you walked in the room, or there's always natural variation. The question is, how big is that variation? How much? And since what that really says is I can't accept any test as absolutely positively foolproof. Every test has errors to it, some sort. The question is, what kind of errors and which way am I error in this thing? Because if I get a test that gets where I have almost 100% correct things on identifying people who are depressed, then what's going to happen is I'm going to identify more people as being depressed who really are not. If I'm absolutely correct on every person who is not depressed, then that means I'm going to lean towards coming up with scores that says, nope, this person's not depressed. It's going to be really tough things to prove. But if my test gets every one of the not depressed people correct, then I'm also going to diagnose some people. I'm going to say some people who are depressed aren't. It's going to lean that way. Type 1 and type 2 errors tend to be in, they're related in the opposite ways. I'm blanking the language of that right now. There's an inverse relationship between those two. As one goes up, the other goes down. This is a really important concept because one of the things we're looking for here, the way we end up deciding something is true, is a thing called the rare event rule. If something is really unusual and doesn't happen very often, we assume something else is going on. If I look out for the front of my house, and typically in front of my house, I have a car goes by my house every 5 minutes on average. And I look out one day and there is 30 cars per minute going by my house. That's unusual. And I can legitimately assume something's going on. Something different has happened here than what is typical in the world. If I find a difference between two things that is unusually different, then I assume there's something underlying this, that really these things are different. The more rare something is, the more when something occurs under controlled conditions, then the more likely it is there's something real going on here. We're looking for those rare events, and the rare events under the null hypothesis are the things we accept as true. One of the things I want to note down here is type 1 errors are generally designated with the alpha down here. Type 1 error down the low center. Type 1 errors are used with an alpha. Type 2 errors are typically done with a beta as the Greek letter associated with it. What we do in statistics is when we do experiments, we set the alpha. It's possible to set beta, but it's much harder, much more confusing. Generally, we go with the alphas. We decide how often are we willing to accept rejecting the null hypothesis when it's really true. Typically in statistics, we take 0.05 as that level. If something happens and it's one of those, that sort of thing only happens 5 times out of 100, we assume something's going on here. Now people use smaller numbers for that. Sometimes people, if it's really important, you want to use a 0.01. If it's not so important, you might use a 0.10 as your alpha. But alpha is the level of risk that we're taking, that we're going to assume we're going to reject the null hypothesis when in fact the null hypothesis is true. That's what we're looking for in the process. Now, how do you decide that? Well, that's an interesting question. Question comes down to risk. What are you risking with something? Let me go back to the use of the PHQ-9, which is a depression screening instrument. If I use that PHQ-9 with 100 people who come through the door of my clinic, and 5% of the time I say, you look like you're depressed, and the person goes, nope, I'm not. 95% of the time, they are, 95% of the time I'm correct in this one, but 5% of the time I'm assuming that you're depressed when you're not really. What's the consequence of that? Well, typically the consequence of that is because I've asked the question, you say, no, I'm not, and we talk for an extra 2 to 3 minutes. Big deal. Doesn't matter a whole lot. Let me go the other way, however. I give you a PHQ-9 and it says you're not depressed and you really are. That's a type 2 error. What happens is you walk out of the clinic depressed with nobody knowing about it but you. There's a cost to that, to you. And that cost is you feel bad. The people around you may feel pretty bad. You might commit suicide. You may not be able to go to work. I mean, there's all kinds of negative consequences. The cost of a type 2 error is potentially pretty high. It's a pretty significant error problem. The cost of a type 1 error, I spend an extra 2 minutes talking to you. Now, if I'm going to decide which of those two things I want, I'd rather have a type 2 error. I'm willing, I would take I would take a type 1 error as being pretty small. No, actually, I do it a type 1 error as being fairly large. I'm willing to accept the fact that I'm making mistakes. I'd rather have more people that I say, are you depressed when you're not, than not asking the question when you are depressed. Because the cost of missing depression is much higher than my making a misjudgment at the front end. Let me take that a little bit further. Let me give you another example of that. Suppose what I'm doing is, instead of a PHQ-9, I'm doing a test for Ebola. That's called the plague, because it's a fairly serious disease. Now, I give the test, and the test comes up positive or comes up negative. If it comes up positive, then see, my assumption with the Ebola test is you do not have Ebola. Truthfully, in this country, I don't think anybody has Ebola at the moment. I just heard some rabbits might, but people don't have, but Ebola is a very serious illness. If I give a test for Ebola, my assumption is you don't have it. That's my working null hypothesis. The alternative hypothesis is you do. Do I want more of a type 1 error or a type 2 error? Well, if you think about it, so if I give you a test and it says, yeah, you look like you might have Ebola, all right, then we immediately start medical treatment with you. Or we give you a second test to see whether the first one's correct. But we could get at some stuff right away. If I test you, I accept that, nope, you don't, the test comes back negative, but you walk out the door and you actually have Ebola. Ebola is not one of those very contagious, very serious diseases. And what happens, you walk out the door and you infect 5 people within a week. Now, 5 people have it, and so if I'm going to make an error here with Ebola, I'm much more interested in the type 1 error. I'd rather think you have it when you don't than miss it when you do, because the consequences of missing it are dramatic. They are profound. Let me go a different way going at this one. Suppose, for instance, that I have a new test for COVID-19. A test whether or not you have COVID-19. Well, people would like to know that if they do. But what happens if you pass the test is your next step in the process is you immediately start treatment for something, and the treatment costs $10,000 per person. Ooh, hmm. Well, now that changes the reckoning here. If you come up with a positive for the COVID-19, what happens? Well, a couple things happen. One is you have to quarantine for some period of time. They wait and see whether the symptoms really do show up. Or you have to take a second test. Those two things are relatively minor consequences. If the treatment costs $10,000, that's not a minor consequence. What's the consequence if I say I accept the null hypothesis, which is that you don't have COVID-19 and you really do? Well, death's a possibility there also, but it's a fairly small possibility. Most folks who get COVID-19 never die. Some do, but most do not. So the question is, which one would you rather have, a type 1 or a type 2 error? I think I would go with a smaller alpha there and a larger beta. Personally, I'd be more likely to accept the likelihood that somebody has COVID-19 except that they don't have it when they really do. I'd be more likely to accept that than I would assuming that they have it when they don't. But if the next step costs $10,000 a person, because you think about administering that to 1,000 people, if 5% of them, that's 50, have a type 1 error, and that's $50,000 it costs me as a next step. That's a fairly high, it's like, there are tests like that. There are medical tests like that what happens is the next step in the process, if you test positive, is you have a serious, significant investment of time and energy and money and treatment. In that kind of situation, well, take one of those, the tests for colon cancer. Colon cancer is one of those diseases that if you get it, you typically have a fair amount of time to treat it. It's not most cases, not all, most cases of colon cancer tend to be relatively slow spreading. So unless you've caught it at a fairly late stage, you've really got some time with colon cancer. But if the next step is, and after it's diagnosed, is a fairly extensive and expensive medical treatment, then I'd be more likely to have a smaller alpha. I'm less likely to want to have a place where I'm assuming you have it when you don't. Then the cost for that would be relatively high. Assuming that you have colon cancer when you do not might subject you to some fairly significant expenses and time. Assuming that you don't have it when you do doesn't seriously impact, as long as there's a reasonable next step in it, doesn't seriously impact your chances for survival. So I was say, rather than have another starting treatment, I'd say, let's go ahead and have another test. Let's try it again and see if we have come up with a positive a second time. We got time. This kind of thinking is how you start thinking about what size alpha do I want to have here? And that's an important question. It's the size of alpha you're looking for in a situation. Let me talk a little bit further here about this rare event rule. One of the questions, this is your normal curve. What's the chances of something happening? Well, at 1 standard deviation, plus or minus 1 standard deviation from the mean, there's a 68% of the chance, 2 out of 3 basically, it's going to happen in that situation. If you get more than that out, then the odds go down. The further out you get on each end, the smaller the probability of that thing happening. And when you get out to 2 or 3 standard deviations, or 3 standard deviations, 99.7% of the cases are within 3 standard deviations. So if you get something where you get a Z-score on something, a 3.2, it's like, that's pretty rare. I mean, that's less than 1 in 1,000. That's about 1 in 1,000 at that point or something. When you construct your null hypothesis, the wording of it tends to be pretty important. For instance, let me suggest that I'm looking at students that I've had in my class for some period of time. And I say, you know, I think there are real gender differences in my class about how people do. My null hypothesis would be there are no gender differences between them. There are no gender differences in terms of how people do in my class. What that would be is the average score for men in my class is the same as it is for women. You know, with some variation of that. No differences. Or this average score for men minus the average score for women is roughly equal to 0. Some amount of variation, but not much. That would be a null hypothesis. And what I'd be looking for there is either men do a whole lot better than women, the left-hand side, or women do a whole lot better than men, the right-hand side. That would be a two-tailed test, where I would say, I don't really know, ever have any intuition one way or the other on it. I just think there's a difference. Gives me a likelihood of a two-tailed test. On the other hand, what I might end up saying is, you know, having looked at this thing for 5 or 6 years, I've been teaching this class, I think women usually do better than men in my class. My null hypothesis in that situation would be the average score for women in my class is greater. No, my null hypothesis would be, again, that the average score for men is equal to or greater than it is for women. I don't think that's true. I think it goes the other way. This is an example. Don't believe that I really believe that. I don't have any basis for that at all, truthfully. But the difference is, in one case, I'm saying, do I get any difference? Men greater than women, women greater than men. Or do I go like this and say, my hypothesis is the women do as well, that men do as well as or better than women do in the class. My alternative hypothesis is women do better than men. This would be a one-tailed test. Why would I do one rather than the other? Well, first of all, it depends on what I'm checking out, what I want to know about. I give an example in the chapter about changing the color of the labels on beer cans, for instance. Well, I'm doing okay with the color I currently have. The question is are the new beer cans, the ones that are proposed, do they do better than what I've got right now? Or do they do the same? And if it's better or the same, if the old color does better or the same as the new color, then I don't want to change. What's the point? The only reason I would change would cost me money if I change the color of the cans, would because the new color would get a better response from customers than the old color. If it does the same, if people look at red cans versus green cans and they're going to go, it doesn't matter to me at all, then it doesn't affect sales. then why would I change? There's no reason for it particularly. The only thing I'm interested in is the new can colors really make a difference in sales. That would be for me a one-tailed test. I don't care if the old color does the same as a new one, or I don't care from hypothesis testing whether the old color does worse, does better than the new one. I'm just testing to say, is the new color better? My null hypothesis is the new color of cans is not better than the old color. That's my null hypothesis. Like if I can disprove that, then I'll change colors of the can. This is one of the crucial pieces here is thinking about is, do you use a one-tailed or do you use a two-tailed test? Let me take a step back here. Throwing a lot of stuff at you, and I appreciate that. Some key things. You start off by figuring out what's your null hypothesis. What do you believe that you want to try and disprove? Second thing is what you do is you look at, okay, so what's my alternative hypothesis? What am I actually trying to prove here? You always got to start there. Always start there. That's the first step. Then what you got to think about is, what are the consequences if I'm wrong? And there's the type 1 wrong and type 2 wrong. Alpha, the number you set when you do a test, is the numbers of type 1 errors that you make. What's the consequence if I accept my null? What's the consequences of rejecting the null hypothesis when it in fact is true? That is, what are the consequences of saying, yep, see this is true, folks, when it really isn't? There's a lot of stuff going on right now in the field of psychology about that we have had a lot of experiments that have actually, looks like they're not replicable, which tends to suggest that we have a lot of type 1 errors in psychology. We have accepted things as true when they really are not. There's a lot of controversy about that right now in the field. But deciding the size of the alpha is a crucial piece for setting up your experiments, because we will use alpha a lot in our computations as we go forward. A third piece, so you're making some decisions about the size of alpha. The third piece you're thinking about is how you state your null hypothesis. Are you interested in a difference, or are you interested in a difference in a particular direction, either greater than or simply less than? If you're just interested in whether there's a difference, it's like A minus B is equal to 0. That's your null hypothesis. Alternative A minus alternative B gives you 0. It doesn't give you a difference at all. It does. Yeah, I'm assuming the null hypothesis, there's no difference between those two things. So if I get a significantly greater or significantly less, those things allow me to reject the null hypothesis. One-tailed or two-tailed? Which one do you want to do? Which one? And that's ultimately a design issue in your head. The reason you make the decision about one-tailed or two-tailed is if you're looking at 5% and you're only looking at 5% on one chance, it gives you a better chance of finding something. There's a bigger area on the right-hand side if you're only doing a one-tailed test. If you got 5%, on one end, it's this big. If you say no 5% on both ends, then it's like, okay, then they both have to get smaller. So the chances of finding that big a difference is a smaller thing. So it's a decision, it's a design decision, basically, as you're choosing to experiment on things. I'll just say this briefly because we're going to get into this later, much more in the next chapter. The third issue is how big a sample do you use? The whole point from inferential statistics is I start with a sample. I'm trying to infer something to the population, to the larger number. The question is, with a small sample, you tend to have a lot more chance for error. Bigger sample, you have a less chance. Bigger sample. And there's an interaction between the size of the sample and the size of alpha. But I'll get into that more in the next chapter. So that's briefly an introduction to the material for this week about hypothesis testing.